So, hello everyone. Today we are going to discuss some problems from Tomato, that is test of mathematics at the 10 plus 2 level. So, we're going to discuss certain subjective problems, mainly related to the topic of polynomials. Uh, okay, so here's the first problem. As you can see, I have numbered the questions according to the number in the book. So this is P68. It has two parts. The first part, uh, determine M so that the equation, a 4-degree equation is given. And so we have to determine M such that this has 4 real roots in AP. So, okay, first of all, let's write down this equation. So the given equation is something like x to the 4 minus 3m plus 2 times x squared plus m squared. So what does fundamental theorem of algebra give us? It tells us that this has exactly, so uh, fundamental theorem of algebra implies P has exactly 4 roots in complex numbers, right? We are not assured anything about real roots or anything. So we have to find them such that these roots are all real and they are in AP. So we assume that the roots are in AP, assume that the roots are in AP. So um like okay, so this is a here's a problem. Now you can take anything, like you can take this sequence A plus D, A plus 2D, A plus 3D. You can take any other like A minus 2D, A minus D, like this. But uh, for our example, we are going to take one certain type of A. That will help us because, okay, so let's see first. Right. So mm, let the roots be alpha 1, alpha 2, alpha 3, alpha 4, right? And so notice that the coefficient of x is cube is 0. So therefore, by beta's relations, what we get is alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 equals 0. So like the best way to choose this AP is if we take A minus 3D, A minus D, A plus D, A plus 3D. Because this is like this is symmetric with respect to D, and the D's will cancel out when we add them. So in fact, we get, so this is optimal to assume, optimal AP to assume. Uh, like You can assume something else also. You'll get the same answer. Just so implies 4a. All the d's cancel out. Equals 0 plus a equals 0. So basically the roots are minus 3d minus d d 3. Okay. So again, sum of roots. Okay. Over here we have used sum of roots. Now we will use product of roots. Right. All the product of all four roots. Again by beta relations. So uh, we get that 9d to the 4 equals m squared, right? Because um, yeah, so just 4, 3, 2, 1, 0. So this is negative, this is positive, this is negative, this is again positive. So constant term will remain as it is. So 0, yeah, so I will just write minus 0 by 1. M squared implies d squared equals root over f by 3 whole squared equals mod of m by 3. Now, this is a part where people are likely to make mistakes. People are likely to assume that d square equals just m by 3, but nowhere in the question has it been given that m is positive or negative. So we have to take mod because the LHS is strictly positive, greater than non-negative, d squared. So we have to take mod m by 3. Now, we are given another coefficient, the coefficient of x, which is minus 3m plus 2. And the sign is again positive. So, okay, just write, let us write down again by beta relations, we get minus, so this is product of roots taken two at a time, right? So it will start with minus 3d, my bad. Minus 3d times minus d plus minus 3d times d. I'll just write down the roots again. Minus 3d minus d plus minus 3d times 3d plus minus d times d plus minus d times 3d plus d times 3d. Right. Uh, let's see if the calculation is correct. So this will in fact be equal to minus of 3m plus 2. So my calculation is correct. So this cancels out. Minus 9. I think something is wrong. Let's check once. Or no. It's up. So this needs to cancel. So we have this my minus 10 d squared equals minus of 3m plus 2. So here again, what we got was this thing. Uh, let us substitute this d squared. So 10 times mod m equals 9m plus 6, right? So we get that m equals 6. This is if we take plus m, and if we take minus m, then we get uh, minus 6 by 19. So you can just check this. Minus 10m equals 9m plus 6. So you just do this and we'll get minus 16. It's minus 6 by 19. Right. So now the problem is half complete. So what have we done is we've assumed that the roots are in AP, and we have showed that if the roots are in AP, so let me write it. So therefore, roots in AP implies m equals 6 or minus 6 by 19. Now we have another condition to check, right? We have to check the real condition. So basically, if the roots are complex, complex roots can still be in AP. Still, we will get these values only. So now we have to check that corresponding to these values, are the roots real or complex? So basically, let us write down this. This was the mother equation. 2 squared m squared equals 0. So this can be written as a quadratic in x squared. So m equals 0. So if we take out the roots, we get is positive negative root under uh, plus 2 squared minus 4m squared by divided by 2. Right. So now what we need is all four roots of x to be real. Now what can happen is, like, this is a real like the 4-degree equation can have three possibilities: all four roots real, all four roots complex, or two real, two complex. So these are the three possibilities. So we only need the one where all the four roots are real. So for that case, we need x squared over here. So x to be real, so we need both of these roots to be positive. So basically both these have to be greater than 0 for our condition to satisfy, right? All right. So basically now notice that, notice. So I mean, it follows from here that so if both of these are positive, then all four values of x will be, from here we will get 2, and basically, like, x is okay, I'll show. So 3m plus 2 is greater than 0, greater than 2 squared minus 4. So you can see this, this directly follows if you just square both sides. Now what you do is, so implies 3m plus 2 minus this thing is again uh, this thing is again, so this thing is clearly greater than 0, and the positive will be anyway greater than 0 if uh, like 3m plus 2 is greater than 0. So we have got two values, 6 minus 19. So two things we have to check. First, we have to check that the discriminant is positive for both these values. So what is the discriminant? So it's 3m plus 2 whole squared minus 4m squared becomes m plus 2 times 5m plus 2. So for 6, it is pretty trivial. And for minus 6 by 19, this becomes greater than 0. Yeah, it becomes greater than 0. So this becomes 38 plus so minus 6 by 19. Am I correct? That's, yeah, into at m equal to minus 6 by 19. So this part is pretty trivial. And this is also, this will be clearly greater than 0 again. So something greater than 0. So this is done. Uh, this is discriminant check. So now we have to check 3m plus 2. So again, for 6, it is pretty trivial. And greater than 0. And 3m again for this thing also is something like uh, 20. That's minus 18 by 9 plus 2. So this becomes 20 by 19, right? Yeah. This is again greater than 0. So basically, we can see that for both of these values, we get that all four roots are real, right? So both of them satisfying. So, okay. Therefore, 6 and m equal to minus 6 by 19 both satisfy. Right. Let's move on to the second part. And in fact, the problem, yeah, so checking the solutions is extremely necessary. Like just finding the solutions, like I showed, it only proves one side of this thing. So for, yeah, one side. So we needed to show this other side also, right? And we just did that. So second part goes something like this. Let a and b be two real numbers. If the roots of this equation, this quadratic, have absolute value less than 1, show each of the following conditions. Right. So we have to prove these things, assuming that the roots, mod of the roots is less than 1. And for here, you cannot assume that the roots are all real or anything like that. Roots can be complex as well. And we know that the absolute value of a complex number is modulus. Right? So we will assume two cases. So this is 2. So fx equals x squared minus ax minus b. Uh, so case 1. Okay, so case 1 is imaginary part of roots is greater than 0. Now we again know that we know that in a polynomial, yeah, in a real not yeah, real, I mean, okay, polynomial with real coefficients, uh, complex roots occur in pairs. Occur in conjugate pairs. So this is a theorem. You can look it up or you can prove this by yourself. Conjugate pairs. So uh, let the roots be C plus ID C minus I, right? Where D is greater than 0. So first part, 6. First part was to prove that mod B. Okay, so by Vita's relation, so I'll just write VR, okay. By Vita's relations, we get, what do we get? So we get 2C equals A, right? If you add them, you get A, and you again get uh, C squared plus D squared. This becomes minus of B, right? And we know that uh, C square plus D square is a, so C and D are both real, right? So over here we'll assume C and D to be real. All right, so we know that greater than 0. Basically, this is strictly greater than 0 because, oh, doesn't matter. Okay. But this is strictly less than 1 because it is given that the modulus is this modulus of the roots is this thing. This is strictly less than 1. This is given to us. We have assumed this given. This implies minus b greater than equal to 0 less than 1 implies b less than equal to 0 greater than minus 1 implies mod b strictly less than 1. First part is done. Second part is second part. So this is the set. We have so minus 2c equals minus a c square plus b square equals minus b. So in fact, we can say minus of a plus b equals. So this thing goes like c squared plus d squared minus 2c. So this thing can be written as c plus 1. Oh, sorry, whole squared minus 1 plus d squared, right? So we can say that this is strictly greater than 0. Why strict? So, where, sorry, no, sorry, my bad. Strictly greater than -1. Why strictly? Because, so basically these are perfect squares, so they will sum up to at least 0. So, and this is -1, so this is greater than, and remember that we had assumed b is strictly greater than 0. So this makes us, uh, so this is how we can make this claim that this is strictly greater than -1. So this implies a plus b, reverse the sign and reverse the inequality sign and the minus sign. So this is part 2 proof. Part 3 is again same type. So b minus a can be written as minus t square minus t squared and minus 2. So this can be written as minus of c plus 1 whole squared minus t squared and plus 1, right? And this is strictly less than 1 because, so this is because 1 minus b square is strictly less than 1 plus c plus 1 whole square, right? This is true, right? Because 1 minus d square is anyway less than 1, right? And this is anyway greater than 1. RHS, this is greater than 1. This is less than 1. So this is anyway true. So we have from here, we can say that b minus a is less than 1. Right. Now, the real case. So case 2, imaginary part equal to 0. So let the roots be alpha, beta, and we know that we know that mod alpha, mod beta, both are less than 1. We also know that alpha beta equals minus b by beta's relations. So, so from here it's pretty trivial that mod alpha beta equals mod b less than 1. So 1 is done. Now part 2 and part 3, there's an interesting way. So you can again like expand alpha beta as the roots of quadratic equation, and you can do that way, but let us do it this way graphically. So basically the graph of a quadratic equation is a parabola, and since it has two real roots, it will intersect the x-axis twice, right? And all the roots are in between 1 and -1. So what we can say is that the functional value at 1 and -1 are both positive terms, right? Because the roots have appeared in this interval, inside this interval, and since the coefficient of the leading term x square is positive, it will be an upward parabola. So we can assume that, like not assume, but this is in fact true. So therefore, f1 greater than 0, f minus 1 greater than 0. This tells us that 1 minus a minus b greater than 0 implies a plus b less than 1. So 2 is done. And this tells us 1 plus a minus b greater than 0 multiply 3 minus a less than 1. 3 is done.